Section 1 Introduction. We're going to talk about deep reinforcement learning, which is primarily driven by online reinforcement learning (RL) algorithms. These algorithms require agents to interact with their environment to learn and explore. They've been successful in various areas like Atari, Go, StarCraft II, Dota 2, and robotics. However, their need for extensive interaction and exploration makes them unsuitable and potentially unsafe for many real-world applications. On the other hand, in an offline setting, agents learn from a pre-existing dataset, which could have been created by humans or other agents. This offline approach could make RL more applicable in real-world scenarios. However, most offline RL benchmarks, such as D4RL and RL Unplugged, have primarily focused on simpler environments with data generated by RL agents. We need more challenging benchmarks to progress towards more complex real-world applications. To address this, we're introducing AlphaStar Unplugged, an offline RL benchmark that uses a dataset derived from millions of human-played StarCraft II game replays. StarCraft II is one of the most complex simulated environments, with elements like partial visibility, randomness, large action and observation spaces, delayed rewards, and multi-agent dynamics. Mastering this game requires strategic planning over long periods and real-time low-level execution. Any advancements in AlphaStar Unplugged could potentially revolutionize other offline RL settings. Unlike most RL domains, StarCraft II has an independent leaderboard of human players with a wide range of skills, providing a rich source of data to train and evaluate offline RL agents. With this paper, we're releasing the most challenging large-scale offline RL benchmark to date, including the code for standard agents and data processing software. By removing environment interactions from the training loop, we've significantly reduced the computational demands of StarCraft II, making it more accessible to a larger number of AI researchers. Our experiments on this benchmark suggest that the top-performing algorithms on smaller-scale benchmarks don't perform well here. For example, return-conditioned behavior cloning, Q-function-based approaches, and algorithms that perform off-policy evaluation during learning often fail to win even a single game against our weakest opponent, and all fail to outperform our unconditional behavior cloning baseline. However, we've also gained insights on how to design successful agents. So far, our most successful approaches are the so-called one-step offline RL approaches. Generally, our best-performing agents follow a two-step process. First, they train a model to estimate the behavior policy and behavior value function. Then, they use the behavior value function to improve the policy, either during training or inference. We believe sharing these insights will be valuable to anyone interested in offline RL, especially on a large scale. Section Summary. In the introduction, the authors highlight the limitations of online reinforcement learning (RL) algorithms and the need for offline RL benchmarks in real-world applications. They introduce AlphaStar Unplugged, an offline RL benchmark derived from replays of humans playing the complex game of StarCraft II. The authors emphasize that breakthroughs in this benchmark could have significant implications for other offline RL settings, and they provide insights on successful agent design, particularly the use of one-step offline RL approaches. Section 2 StarCraft II for offline reinforcement learning. In this section, we're discussing the use of StarCraft II, a real-time strategy game, as a platform for offline reinforcement learning. Players of this game compete for control over a shared map by gathering resources and building units and structures. The game offers various modes, including team games and custom maps. One such mode, the StarCraft Multi-Agent Challenge, has become a popular testing ground for multi-agent reinforcement learning, featuring a set of specific tasks. In our study, we're focusing on StarCraft II as a two-player game, which is the most common way to play. This mode is enjoyed by all types of players, from casual gamers to professional esports athletes. It requires strategic thinking over extended periods and quick decision-making for managing units. The game offers a variety of strategies, each with its unique challenges, especially considering that players can choose from 3 different alien races, each with its own unique mechanics, strengths, and weaknesses. The game's strategies can also be influenced by the different terrains offered by the various maps. StarCraft II is an excellent platform for developing and testing offline reinforcement learning algorithms. It has been played online for many years, and millions of games have been recorded and can be used to train AI agents. These agents can then be evaluated by having them play against humans, including professional players, built-in bots, community-created bots, or even advanced online reinforcement learning agents like AlphaStar or T-Starbot. However, StarCraft II also presents some unique challenges for offline reinforcement learning. One of these is the action space. The performance of algorithms learning from offline data heavily depends on the variety of state action pairs available in the data. We refer to this as coverage. The more state action pairs are missing, the more challenging the problem becomes. In StarCraft II, the action space is highly structured. The agent must choose an action type, select a subset of its units to perform the action, choose a target for the action, and decide when to observe and act next. In our API, we estimate there are about 10 to the power of 26 possible actions per game step. This is significantly more than the 18 possible actions per step in Atari games, making it nearly impossible to achieve high-state action coverage in StarCraft II. Another challenge is the stochastic environment. Stochastic environments may require many more trajectories to achieve high-state action coverage. While the game engine itself has a small amount of randomness, the main source of uncertainty comes from the unpredictable strategies of the opponent, which are typically not deterministic. This is in contrast to the Atari environment, where randomness only comes from sticky actions. StarCraft II is also a game of imperfect information. Players only have information about opponent units that are within their own unit's field of view. This necessitates scouting, or sending units around the map to gather information about the current state of the game, which may be needed later. This is different from Atari, where remembering the last 3 frames is usually enough. Finally, we have access to a dataset of millions of human replays for StarCraft II. These replays showcase a wide and diverse range of exploration and exploitation strategies. This is in contrast to existing benchmarks, which tend to be biased towards datasets generated by reinforcement learning agents. Section Summary. StarCraft II is a complex real-time strategy game with various modes and challenging properties, making it an ideal environment for developing and evaluating offline reinforcement learning algorithms. The game's highly structured action space, with approximately 10 to the power of 26 possible actions per game step, poses a significant challenge in achieving high-state action coverage. Additionally, the stochastic nature of the game, influenced by the unknown opponent policy and the partial observability, where players need to scout for information, further contribute to the complexity. However, the availability of a large dataset of human replays provides a diverse range of strategies for training and evaluation purposes. Section 3. AlphaStar Unplugged. We're introducing AlphaStar Unplugged as a new standard for offline learning in the game StarCraft II. This project builds upon the existing StarCraft II learning environment and the AlphaStar agents, adding several key components necessary for an offline reinforcement learning benchmark. These include 1. A fixed dataset and training rules to ensure fair comparisons between methods. 2. A set of metrics to evaluate agent performance. 3. A selection of well-tuned baseline agents. 4. Open source code. Creating an agent that performs well in StarCraft II is a huge task, so we're providing a well-tuned behavior cloning agent that forms the basis for all agents discussed in this paper. We've also open-sourced our architecture, data pipeline, dataset generation scripts, and supervised learning agent. Our dataset consists of about 20 million publicly available StarCraft II games. However, due to technical reasons, we've limited the data to versions 4.8.2 to 4.9.2 of the game, leaving us with nearly 5 million games. These games come from the StarCraft II ladder, the official matchmaking mechanism. Each player is rated by their matchmaking rating, MMR, a ranking system similar to the ELO rating system in chess. The MMR ranges from 0 to 7,000. To ensure high-quality training data, we only use games played by players with an MMR greater than 3,500, which represents the top 22% of players. This leaves us with about 1.4 million games. Each game provides 2 episodes from a machine learning perspective, 1 for each side in 2-player games. This gives us a total of 2.8 million episodes. These episodes represent more than 30 years of gameplay and are played across 2 different balance patches and 10 different maps. The average 2-player game lasts about 11 minutes, which equates to roughly 15,000 internal game steps. This presents a significant modeling challenge, making training more difficult and time-consuming. To address this, we only observe the steps when the player took an action, reducing the effective length of the episode by 12 times. Each episode also includes metadata, such as the game outcome, 1 for a win, 0 for a draw, and -1 for a loss, and the MMR of each player. The games were played online using Blizzard's matchmaking system, which ensures that in most games, both players have a similar MMR. The data is anonymized and does not contain personal information about the players. The full dataset represents over 30 years of gameplay, amounting to 21 billion internal game steps, or 3.5 billion training observations. Section Summary. AlphaStar Unplugged is proposed as a benchmark for offline learning on StarCraft II, providing a fixed dataset and training rules for fair comparison between methods. The dataset consists of approximately 1.4 million games played by top-ranked players, spanning over 2 different balance patches and played on 10 different maps. The average game is about 11 minutes long, but trajectories are shortened by only observing steps when the player takes an action, cutting the effective length of the episode by 12 times. Section 3.2 Training Restrictions. In Section 3.2, we discuss the limitations we impose during the training phase. We restrict the algorithms from using any data outside of the dataset mentioned in section. Specifically, the environment is not allowed to gather additional data. However, we do permit online policy evaluation, meaning that we can test the policies in the environment to assess their effectiveness. This can be particularly helpful for fine-tuning hyperparameters. Unlike the original AlphaStar agents, our agents are trained to play all 3 races in StarCraft II. This presents a greater challenge, as agents usually perform better when trained on a single race. Additionally, they are trained to play on all 10 maps included in the dataset. In our experiments, we aim to use the same number of training inputs whenever possible, roughly around 10 billion observations in total. This makes the results easier to compare. However, this is not a strict rule but rather a guideline. The final performance achieved after each method has reached its saturation point is a meaningful metric for comparison, provided each method was given sufficient computational resources. In Section 3.3, we discuss the evaluation protocol. There are many metrics that can be used to assess the agents. The simplest, yet least informative, is to examine the value of the loss function. Conversely, the most informative, but also the most challenging to compute, would be to evaluate the agent against a broad range of human players, including professional ones. In this paper, we propose a middle ground. We assess our agents by having them play repeated games against a fixed group of 7 opponents, including the very_hard built-in bot and a set of 6 reference agents. During the training phase, we only evaluate the agents against the very_hard bot, as it is significantly less resource-intensive. We primarily use this as a validation metric to fine-tune hyperparameters and eliminate non-promising experiments. Fully trained agents are evaluated against the full set of opponents mentioned earlier, on all maps. We then compile these win rates into 2 aggregate metrics, ELO rating and robustness. Robustness is calculated as 1 minus the lowest win rate over the set of reference agents. More details on the computation of these metrics can be found in the appendix. Section Summary. During training, the algorithms are restricted from using any data beyond the dataset provided, but they are allowed to evaluate policies in the environment to measure their performance. The agents are trained to play all 3 races of StarCraft II and on all 10 maps available in the dataset. The evaluation protocol involves playing repeated games against a fixed selection of 7 opponents, including the very_hard built-in bot and 6 reference agents. The agents are evaluated against the full set of opponents on all maps, and the win rates are combined into aggregated metrics such as ELO rating and robustness. Section 4 Reference Agents. In this section, we'll delve into the specifics of the 6 reference agents we've developed. These agents serve as both benchmarks and evaluation tools. We'll explain the methods and algorithms we use to train them. You can find the technical details in the appendix and the results in a later section. Let's start with some definitions. We're using a game called StarCraft II as our testing ground. The game's dynamics can be described using a Markov decision process, MDP. In simple terms, an MDP is a mathematical model used in decision-making where outcomes are partly random and partly under the control of a decision-maker. In our case, the MDP consists of a set of states and actions, a transition distribution that describes the probability of moving from one state to another given a certain action, and a reward function. In StarCraft II, the reward is 1 if you win, -1 if you lose, and 0 otherwise. It doesn't depend on the action taken. There's also an initial state distribution that describes the probability of the game starting in a certain state. In the offline setting, the agent learns from a dataset of episodes, which are sequences of states and actions. A policy is a probability distribution over the actions given a state. The dataset is assumed to have been generated by following an unknown behavior policy. In StarCraft II, the agent doesn't observe every step of the game. We call the number of game steps between 2 observed steps the delay. This corresponds to the amount of real time elapsed between the 2 observations. The delay must be part of the action because the environment needs to know how many steps to skip until the next observation. We define the expected discounted return as the expected sum of the discounted rewards obtained if we follow a certain policy from a certain state. The discount between two steps is based on the delay between the steps. In StarCraft II, the reward is the win-loss signal, so it can only be non-zero on the last step of the episode. The goal of offline reinforcement learning is to find a policy that maximizes the expected discounted return. During training, we refer to the policy trained to estimate this optimal policy as the target policy. We use different symbols to denote the value functions for the behavior and target policies, which are trained to estimate the expected discounted return for these policies. We typically train the agent on sequences of up to k consecutive time steps, assembled in a minibatch of m independent sequences. Unless specified otherwise, the minibatches are independent from each other, such that two consecutive minibatches are not correlated. Section Summary. In this section, the authors introduce a set of 6 reference agents that can be used as baselines and for evaluation metrics in the context of StarCraft II. They provide details on the methodology and algorithms used to train these agents, with implementation details in the appendix and results in a later section. The authors also define the underlying system dynamics of StarCraft II as a Markov decision process, MDP, and explain the offline setting where the agent learns from a dataset without interacting with the MDP directly. They discuss policies, delays between observed states, and the expected discounted return based on the delay and rewards. The goal of offline RL is to find a policy that maximizes the expected return, and during training, the authors refer to the trained policy as the target policy. They use value functions to estimate the returns for the behavior and target policies. The agents are trained on rollouts, which are sequences of consecutive time steps assembled in mini batches. Section 4.2 Architecture. We've designed all our experiments around a single, enhanced agent architecture, which is an upgraded version of the model we've used in previous work. This architecture is illustrated in a figure in the paper. The raw inputs from the StarCraft II API are organized into 3 categories: vectors, units, and feature planes. Units refer to a list of features for each game unit, while feature planes provide more detailed information. You can find more about this in the appendix. Actions, on the other hand, consist of 7 arguments and can be grouped in a similar way. Function, delay, queued, and repeat are vectors, as each argument is chosen from a single vector of logits. Unit_tags and target_unit_tag are indices in the unit's inputs, and the world action is a 2D point on the feature planes. Our architecture is built around these categories. Each input category is encoded and processed separately using a suitable architecture: a multi-layer perceptron, MLP, for vector inputs, a transformer for unit inputs, and a residual convolutional network for feature planes. Some of these convolutions are stritted, meaning most of the computation is done at a lower resolution. We also embed the arguments of the previous action, except for the world previous argument, as we found this leads to overfitting. We use special operations to allow interactions between these categories. For instance, we scatter units into feature planes, meaning we place the embedding of each unit at its corresponding location on the feature plane. We use an averaging operation to embed the units into the embedded vectors. Feature planes are embedded into vectors using stritted convolutions and reshaping, and we do the reverse to embed vectors into feature planes. We experimented with using memory in the vector category, which could be either LSTM or Transformer XL. However, most of our results do not use memory. For experiments that use a value function, we add an MLP on top of the vector features to produce an estimate of the value function. Finally, we sample actions. The 7 arguments are sampled in this order: function, delay, queued, repeat, unit_tags, target_unit_tag, and world. They are sampled auto-regressively, meaning each sampled argument is used to sample the next one. The first 4 arguments are sampled from the vector category. The next 2 are sampled from the vector and units categories using pointer networks, and finally, the world argument is sampled from the upsampled feature planes. Note that unit_tags is obtained by sampling the pointer network 64 times auto-regressively, so in a sense, unit_tags represent 64 arguments. You can find the exact hyperparameters and details of the architecture in the open source code we've provided. Section Summary. The agent architecture used in our experiments is an improved version of a previous model. It consists of 3 modalities of inputs: vectors, units, and feature planes. Each modality is processed independently using different architectures, such as MLP, transformer, and residual convolutional network. Interactions between modalities are achieved through special operations, such as scattering units into feature planes and embedding feature planes into vectors. Actions are sampled in a specific order, with some arguments being sampled from the vector modality and others from the vector and units modalities. The exact details and hyperparameters of the architecture can be found in the open-sourced code. Section: MMR Conditioning. We condition our model on the matchmaking rating, MMR, of the player who created the trajectory during training. This MMR is given as a vector input. When we want to use the model, we can adjust the quality of the game played by the agent by altering the MMR input. To ensure the agent performs at its best, we typically set the MMR to the highest value. This approach is akin to return-conditioned behavior cloning, where the MMR serves as the reward. For our MuZero experiments, we define a latent space, denoted as L, which is the space of vectors before the application of the multilayer perceptron, MLP, function. We divide the model into an encoder, which maps the state space S to the latent space L, and two decoders. The first decoder maps latent states to distributions over actions, while the second decoder is a value function that maps the latent space L to the real number space R in our implementation. The first decoder only produces distributions for the function and delay. The remaining arguments are derived from the estimated behavior policy. We also introduce a latent model that maps the latent space and action space to the latent space. Given a sequence of states and actions, we calculate the latent state, the action distribution, and the value function for each state in the sequence. Note that the first state in the sequence is not necessarily the first state of an episode. Our first reference agent is trained using behavior cloning, a process that estimates the behavior policy. We learn an estimate by minimizing the negative log likelihood of the action under the policy for a given state. This is similar to training a language model. The same procedure was used by the AlphaStar Supervised agent. In practice, since each action consists of 7 arguments, there is 1 loss per argument. To prevent overfitting during behavior cloning, we also use a weight decay loss, which is calculated as the sum of the squares of the network parameters. Section Summary. During training, the MMR, matchmaking rating, of the player who generated the trajectory is used as input, allowing us to control the quality of the game played by the agent by adjusting the MMR input. In the MuZero experiments, the latent space is defined as the space of vectors before the function MLP, multilayer perceptron, and the model is split into an encoder, 2 decoders, 1 for action distributions and 1 for value functions, and a latent model. The behavior cloning agent is trained by estimating the behavior policy and minimizing the negative log likelihood of the actions under the estimated policy. Section: Fine-tuned behavior cloning, FTBC, agent. We've developed an agent known as fine-tuned behavior cloning, FTBC. This agent works by imitating the training data, meaning that the better the quality of the data, the better the performance of the agent. However, there's a downside. When we filter the data to improve its quality, we end up with fewer episodes, which can affect the agent's ability to generalize. To overcome this, we've introduced a process called fine-tuning. This is a second phase of training that takes place after the initial behavior cloning. During this phase, we lower the learning rate and filter the data to include only the best games. This approach has proven to be more effective than training solely on either the full dataset or the filtered dataset. We also use an approach called offline Actor-Critic. This method involves learning a target policy, denoted as pi, and a value function, denoted as v(pi). In situations where the target policy pi is different from the behavior policy mu, we calculate something called important sampling ratios. These ratios are calculated as the ratio of the probability of action A_t given state S_t under the target policy to the probability of the same action given the same state under the behavior policy. There are many ways to calculate the loss in this context. The simplest method is called one-step temporal differences, or TD0. This method calculates the loss as the negative sum of the product of the important sampling ratio, the difference between the discounted future value and the current value plus the reward at the next state, and the log of the probability of the action given the state, for all states except the last one. The symbol circle d' in the equation represents the stop gradient operation, which prevents certain variables from being updated during backpropagation. The loss can be adjusted to use n-step temporal differences by adding more terms to the equation. It can also be improved by using a method called vtrace to reduce variance. For simplicity, we only applied this loss for some of the arguments, namely function and delay, and we use the behavior policy for the others. We also learned the estimated behavior value, denoted as v(mu), by minimizing the mean squared error, MSE, loss. This loss is calculated as half the sum of the squared differences between the estimated value at each state and the reward at that state. Section Summary. The Fine-Tuned Behavior Cloning (FTBC) agent improves performance by fine-tuning the training data after running behavior cloning on the entire dataset. By reducing the learning rate and filtering the data to top-tier games, the agent achieves better generalization. In the offline Actor-Critic algorithm, important sampling ratios are computed to handle off-policy settings, and the loss function can be modified using n-step temporal differences and vtrace to reduce variance. The estimated behavior value is learned by minimizing the mean squared error (MSE) loss. Section. Offline Actor-Critic (OAC) agent. We're going to discuss the offline Actor-Critic (OAC) agent. The Actor-Critic method has a correction term that allows it to work off-policy, but it needs some adjustments to function in a purely offline setting. The behavior policy, which we'll call mu, is part of the denominator of a ratio called rho. However, we don't have direct access to the behavior policy used by the players. We can only see the actions they take. Luckily, we have a behavior cloning agent that learns an estimate of mu, which we'll call hat mu. We use this estimate to calculate an estimated ratio, hat rho, which is pi divided by hat mu. The behavior cloning policy, hat mu, can be used as the starting point for pi, meaning it's used to set the initial weights. This makes the estimated importance sampling ratio, hat rho, equal to 1 at the start of training. We use v/pi as the critic in our equation, which is a standard practice in Actor-Critic methods. This can be done even in offline settings by using a temporal differences loss for the value function. However, this can sometimes lead to divergence during offline training, which is a known issue. One possible solution is to stop training early. The policy pi improves initially before it starts to deteriorate, so we could stop training early and end up with an improved policy pi. But this method requires running the environment to know when to stop, which goes against the rules of AlphaStar Unplugged. So, we use v/mu as a critic instead of v/pi, and we keep it fixed. Next, we'll talk about the emphatic offline Actor-Critic (EOAC) agent. This agent uses n-step emphatic traces, netted, to avoid divergence in off-policy learning under certain conditions. It does this by weighting the updates beyond the important sampling ratios. Lastly, we'll discuss MuZero Unplugged, which adapts Monte Carlo tree search (MCTS) for offline settings. This method has been successful on a variety of benchmarks. To handle the large action space of StarCraft II, we sample multiple actions from the policy and limit the search to these actions only. This allows us to scale to the large action space of StarCraft II. We use the latent model we discussed earlier, and like the offline Actor-Critic agents, we only improve the function and delay from the behavior cloning policy. Section Summary. The offline Actor-Critic (OAC) agent is adjusted for the pure offline setting by using the estimated behavior policy hat mu to compute the estimated importance sampling hat rho equals pi hat mu. The emphatic offline Actor-Critic (EOAC) agent avoids divergence in off-policy learning by weighting the updates beyond the importance sampling ratios using n-step emphatic traces (NETD). MuZero Unplugged adapts Monte Carlo tree search (MCTS) to the offline setting and handles the large action space of StarCraft II by sampling multiple actions from the policy and restricting the search to these actions only. Section. MuZero Supervised (MZS) agent. We're going to discuss the MuZero Supervised (MZS) agent. Similar to the offline Actor-Critic scenario, the simultaneous training of the target policy, denoted as pi, and the estimated value function, denoted as v/pi, can lead to divergence. To avoid this, we can adopt a similar strategy where we only train the policy to estimate the behavior policy, and use the value and latent model to run Monte Carlo tree search (MCTS) only during the inference phase. This approach only uses the losses for the policy and the value function for MuZero. In simpler terms, the loss is calculated as the sum of the behavior cloning loss, L/BC, and the mean squared error loss, L/MSE. This is represented by the equation L/MuZero S equals L/BC S plus L/MSE S. The policy and value function are computed using the latent model for all steps except the first one. While this loss calculation is similar to standard behavior cloning, it can lead to improved performance due to the regularization effects of the value function training and the latent model. Next, we have the MuZero Supervised with MCTS at inference time, MZS-MCTS agent. The MuZero Unplugged algorithm uses MCTS both during training and inference. As we mentioned earlier, improving the policy during training can lead to divergence. However, using MCTS during inference is stable and results in better policies. In the next section, we'll discuss some experiments. We'll measure the impact of various parameters, using the win rate against a very hard bot as our metric. Most of these experiments are conducted in the behavior cloning setting. Due to the high cost of running these experiments, we were only able to train one model per parameter set. However, the consistency of the results suggests that they are significant. We also present the performance of the reference agents on all AlphaStar Unplugged metrics, as well as against the original AlphaStar agents. In this section, we refer to the number of learner steps as the number of weight updates on mini batches of rollouts of size m times k. The total number of observations used by the learner, i.e., the number of steps multiplied by m times k, is referred to as the number of learner frames. Section summary. The MuZero Supervised (MZS) agent trains the policy and value function together, but this can lead to divergence. To address this, the policy is trained to estimate the behavior policy, while the value and latent model are used only during inference. This approach improves performance by leveraging the regularization effects of value function training and the latent model. On the other hand, the MuZero Supervised with MCTS at inference time, MZS MCTS, agent uses MCTS both during training and inference, leading to stable policies and better performance. The experiments in this section measure the influence of various parameters, using win rate against the very_hardbot as the metric. Section 5.1 Minibatch and rollout sizes. In Section 5.1, we discuss the impact of minibatch and rollout sizes on our model's performance. We found that increasing the product of the minibatch size, m, and the rollout size, k, generally improves the model's performance. However, there are limitations to this approach due to memory usage constraints. The maximum values we could use were either 16,384 or 32,768, depending on the method used. Additionally, for the offline Actor-Critic and MuZero methods, we found that a rollout size greater than 1 was necessary, and larger values helped stabilize the training process. In Section 5.2, we delve into the influence of the learning rate on the performance of our models. We used a cosine learning rate schedule, which was determined by the initial learning rate. In some experiments, we used a ramp in period over a certain number of frames. The learning rate at any given frame was calculated using a formula that involved the initial learning rate, the current frame number, and the total number of training frames. We compared this schedule to a constant learning rate and found that the final performance varied with different initial learning rates and minibatch sizes. However, we noticed that the optimal initial learning rate could change over the course of training. For instance, the best performance after 1 billion steps was achieved with an initial learning rate of 0.001, but this was not the case after full training. In subsequent experiments, we used an initial learning rate of 0.0005 unless stated otherwise. In Section 5.3, we discuss the number of training frames used. Most of our models were trained over 10 billion input frames. We observed that the performance of the models trained on fewer frames increased logarithmically with the number of training frames. However, some of our reference agents, such as the fine-tuned and offline Actor-Critic agents, were trained on an additional 1 billion frames, starting from the behavior cloning agent. This means they were trained on a total of 11 billion frames, while others were only trained on 10 billion frames. Section summary. The size of the minibatch and rollout in training models affects their performance, with larger values leading to better results, but there are limitations due to memory usage. The learning rate also plays a significant role, and a cosine learning rate schedule with an initial learning rate is used. The number of training frames also impacts performance, with logarithmic improvements observed as the number increases. Section 5.4 Dataset size. We've examined the impact of various factors on the performance of behavior cloning, including the size of the dataset, data filtering, and memory implementation. In terms of dataset size, we found that the model's performance doesn't significantly change even when we only use 10% of the episodes in the dataset for training. This is an interesting observation as it suggests that we can reduce storage requirements without significantly affecting the model's performance. However, if we reduce the dataset size even further, the performance does start to deteriorate. When it comes to data filtering, we've noticed that it greatly influences the model's final performance. Specifically, if we limit the training set to fewer, high-quality episodes, the model's performance tends to worsen. However, if we first train the model using the full dataset and then fine-tune it using high-quality data, we achieve the best results. As for memory implementation, we've experimented with different methods, including using an LSTM module, transformers, and no memory at all. Interestingly, we found that not using any memory actually results in better performance for behavior cloning, even though the final loss values are higher. We've also observed that the performance of the memory-less agent tends to plateau after training on 10 trillion frames. On the other hand, agents with memory, such as those using transformers, continue to improve their performance even beyond this point, outperforming the memory-less agent if trained for 20 trillion frames. However, it's worth noting that agents using transformers require extensive hyperparameter tuning and longer training times. As a result, all the agents we've presented in our main experiments are memory-less. We believe that using memory for other offline RL baselines could yield more significant benefits and is a promising area for future research. Section summary. The behavior cloning performance is evaluated for different dataset sizes, and it is found that even with only 10% of the episodes in the dataset, the win rate is close to the best one, which can save storage with minimal cost. However, further reducing the dataset size significantly affects the performance. Filtering the data has a significant impact on the final performance, and training using the full dataset followed by a fine-tuning phase on high-quality data yields the best results. Surprisingly, using no memory performs better than using LSTM for behavior cloning, although the final losses are higher. The transformer agent performs similarly to the memory-less agent on 10 to the power of 10 training frames, but outperforms it if trained for 2*10 to the power of 10 frames. Section 5.7 Model Size. In this section, we discuss various aspects of our model, including its size, temperature and sampling, the critique of the offline Actor-Critic, and the use of Monte Carlo tree search, MCTS, during training and inference. 5.7 Model Size. Our model is quite complex, and while it's possible to scale individual parts, it's not practical. We've chosen a model size that is the largest possible without causing significant slowdowns in memory. If we reduce the model's width by half, the performance drops significantly, from an 83% to a 76% win rate against the very hard bot. However, reducing the model's depth by half doesn't significantly affect the win rate, which remains around 82%. In our experimental setup, reducing the depth doesn't speed up training, but we believe that using smaller models could potentially increase speed in the future. 5.8 Temperature and sampling. During the inference process, we sample from the policy given a state. In practice, the policy is represented by a vector of logits. The policy of an action given a state is calculated as the exponential of the action's logit divided by the temperature, normalized by the sum of the exponentials of all actions' logits. The temperature during training is set to 1, but it can be adjusted during inference to make the policy more focused. We've found that a temperature of 0.8 works well during inference. 5.9 Critique of offline Actor-Critic. For the offline Actor-Critic, we tried using the value function of the target policy as the critic, instead of the fixed value function of the behavior policy. However, we observed a divergence when using the target policy's value function. Although the win rate initially increased in both cases, it remained high with the behavior policy's value function but deteriorated with the target policy's value function. This suggests that the target and behavior policies diverged over the course of training. 5.10 MCTS during training and inference. Our initial experiments with the full MuZero Unplugged algorithm, which involves training with MCTS targets, were unsuccessful. The policy quickly collapsed to a few actions with high estimated values. While using MCTS during inference improved performance, using it during training led to a collapsed policy. We further investigated this by evaluating the performance of repeated applications of MCTS policy improvement on the behavior policy and its value. We found that the performance of this policy was worse than the performance of the original policy or the MCTS enhanced behavior policy. This suggests that repeated applications of MCTS do not continue to improve the policy, likely because the MCTS policy distribution generates out-of-distribution action samples with overestimated value estimates. However, using MCTS during inference consistently outperforms not using it, even at the beginning of training. Section summary. The model size was chosen to be the largest that can fit in memory without significant slowdown, and scaling down the width of the model led to a decrease in performance, while scaling down the depth barely changed the win rate. During inference, the temperature of the policy was set to 0.8 to make it more peaked. Using the value function of the target policy as the critic in offline Actor-Critic led to divergence between the target policy and the behavior policy. Training with MCTS targets was not successful as it caused the policy to collapse to a few actions with high estimated value. Repeated applications of MCTS did not improve the policy further, likely due to generating out-of-distribution action samples with overestimated value estimates. Section 5.11 Evaluation of the reference agents. In this section, we're evaluating our 6 reference agents. We're using 3 different measures to do this: robustness, ELO, and win rate against a particularly challenging built-in bot. We've explained these measures in a previous section. The top 3 agents all use offline reinforcement learning algorithms, which we've highlighted in light blue. You can see the full win rate matrix for the reference agents in one of our figures. We've also provided a more detailed matrix, broken down by race, in the appendix. One agent, the MuZero Supervised with MCTS at inference time, or MZS for short, performs the best. However, it does take longer to make inferences. Generally, the 3 offline reinforcement learning methods rank closely together and significantly outperform behavior cloning. For a more comprehensive comparison, we've also looked at the original AlphaStar agents. The AlphaStar Supervised was trained as 3 race-specific agents, which is different from our benchmark rules that require agents to play all races. So, we've also compared our agents to a version of AlphaStar Supervised that was trained to play all races. The win rates for MZS, MCTS, EOAC, and OAC are 90%, 93%, and 90% respectively. While offline reinforcement learning does improve upon the behavior cloning baseline, it's still far from the online reinforcement learning performance of AlphaStar Final, which was trained using significantly more computing power. In addition to these, we've evaluated several typical off-policy and offline reinforcement learning baselines. These include action-value-based methods like deep offline Q learning, SARSA, critic regularized regression, CRR, batch-constrained deep Q learning, BCQ, regularized behavior value estimation, RBVE, critic-weighted policy, CWP, and return-conditioned behavior cloning, RCBC, on AlphaStar Unplugged. We also tried advantage-weighted regression, AWR, and proximal policy optimization, PPO. However, none of these approaches could outperform the agents such as BC and FTBC. In this section, we'll highlight some of these approaches and the challenges we faced when we scaled them up to StarCraft II. Section Summary. In this section, the authors evaluate the performance of 6 reference agents using 3 metrics: robustness, ELO, and win rate. The 3 best agents utilize offline reinforcement learning, RL, algorithms and outperform behavior cloning. However, these offline RL methods still fall short of the online RL performance of the AlphaStar Final agent, which was trained using significantly more computing power. Additionally, the authors compare their agents to other offline RL baselines but find that none of them achieve better results than their proposed agents. Section: Deep Offline Q Learning. We attempted to train offline Q learning agents based on the Deep Q Network, DQN, model, which predicts Q values and policy using the same output layer for only the function argument. However, these agents proved unstable during training and were unable to win against the very_hard bot. Traditional methods to enhance Q learning, such as n-step returns, dueling network architecture, and double Q learning, did not improve our agents' performance. Furthermore, the accuracy of the action values predicting the returns was poor. We also trained agents using offline reinforcement learning, RL, methods that utilize action values. These agents, including CRR, BCQ, CWP, and RBVE, were trained with an action value Q head on the function argument. CRR and RBVE yielded similar results, but neither significantly outperformed the BC agent. BVE and RBVE were stable during training. All these agents achieved a win rate of around 83 to 84% against the very_hard bot. We also trained a behavior cloning, BC, agent conditioned on the win-loss return, known as return-conditioned behavior cloning, RCBC. However, the agent seemed to ignore the return conditioning, which we believe is due to the inherent challenges of RCBC approaches, such as the unpredictability caused by noisy opponents and the inability to do trajectory stitching. Behavior cloning forms the basis of all our agents. The offline RL agents start by estimating the behavior policy using behavior cloning, then enhance it using the reward signal. This allows them to perform significantly better than the behavior cloning results. However, the policy they learn is a smoothed version of all the policies that generated the dataset. In contrast, offline RL methods use rewards to improve learned policies in different ways. We found that algorithms originally designed for online learning, even with off-policy corrections, do not perform well when directly applied to the full offline RL setting. We believe this is partly due to the problem of the deadly triad. However, recent works have shown that these algorithms can be made more effective by ensuring the target policy stays close to the behavior policy, and that the value function stays close to v_mu, or both. Our results with Actor-Critic and MuZero align with these findings. Among all the methods we tried, the reference agents led to improved performance. However, we also tried several other methods without success. We may have missed the modifications that would have made these methods perform well on this dataset. The AlphaStar Unplugged task is fundamentally challenging due to limited coverage, weak learning signal, difficult credit assignment, and the requirement of learning autoregressive Q values. The action space is very large, the state action coverage in the dataset is low, and the environment is highly partially observable. This makes it difficult for the value function to extrapolate to unseen state and actions. This is particularly impactful for Q values-based methods. The win-loss reward is a weak learning signal to learn a good policy because the dataset has games with a wide range of qualities and the win-loss reward ignores this. Credit assignment is difficult due to large action space, sparse rewards, long horizon, and partial observability. This exacerbates the problems with the offline RL-based agents. The autoregressive action space requires learning autoregressive Q values, which is challenging and understudied in the literature. Section summary. Deep offline Q learning agents based on DQN were trained, but they had unstable training and a 0% win rate against the very_hardbot. Various approaches to improve Q learning, such as n-step returns and double Q learning, did not enhance the performance. Offline RL methods using action values, such as CRR, BCQ, CWP, and RBVE, achieved around 83 to 84% win rate against the very_hardbot. However, the RCBC approach, which conditioned a BC agent on the win-loss return, did not show any noticeable difference in performance. The challenges in the AlphaStar Unplugged environment include limited coverage, weak learning signal, difficult credit assignment, and the need to learn autoregressive Q values. Section 7 Related work. We've seen significant advancements in the field of online reinforcement learning, RL, particularly in its application to computer gaming. RL algorithms have been successful in outperforming human experts in a variety of games, including StarCraft II, Dota, and Atari. Similar progress has been noted in board games like chess and Go. However, the application of offline RL methods, despite their promising results in games like Atari, has not been explored in complex, partially observable games using data from human experts. This is where our work comes in. We've introduced a benchmark for StarCraft II, filling a gap in the current research landscape. There are existing benchmarks for offline RL, such as RL Unplugged and D4RL. RL Unplugged provides a range of task domains with a unified API and evaluation protocol, while D4RL focuses on mixed data sources. However, both of these benchmarks lack tasks that are high-dimensional and partially observable, which is a key feature of our new benchmark. Offline RL is a burgeoning field of research, primarily because it allows us to use existing datasets to learn policies that can be applied in real-world scenarios. There are several methods within offline RL, including policy constraint approaches, which ensure the learned policy remains close to the behavior policy, and value-based approaches, which promote more conservative value estimates through either pessimistic regularization or uncertainty. Other methods include model-based approaches and adaptations of standard off-policy RL methods like DQN or D4PG. Recently, methods that use only a single step of policy improvement have shown to be highly effective in offline reinforcement learning. This is an exciting development in the field and one that we're eager to explore further. Section summary. Offline reinforcement learning, RL, has gained attention for leveraging fixed datasets to learn policies for real-world deployment. Existing benchmarks like RL Unplugged and D4RL lack high-dimensional, partially observable tasks. This paper introduces a benchmark for StarCraft II, filling this gap and providing a suite of benchmarks for offline RL with a unified API and evaluation protocol. Offline RL methods include policy constraint, value-based, model-based, and adaptations of standard off-policy RL methods, with recent success seen in one-step policy improvement approaches.